Let's talk about particles. You think you know what they are, right? You've heard about them your whole life. Electrons, protons, neutrons, tiny pieces of matter, the smallest building blocks. Everything around you is made of them. Your phone, your table, your body. So, you must understand particles. Okay, explain one to me. What is a particle exactly? Where is it? What does it look like? What is it doing right now? Most people answer with something vague. It is a tiny object. It is really small. It moves around. It bumps into other particles. That sounds reasonable. It sounds like a smaller version of the world you already know. But here's what bothers me about those answers. They do not actually describe anything you have ever seen. Think about the last time you encountered a particle. Not in a textbook, not in a diagram, in real life. When have you ever seen one? You have never watched an electron move. You have never seen a proton sitting somewhere. What you have seen are screens lighting up. You have seen little dots appear. You have seen flashes, clicks, traces, noise. Patterns that only make sense after you collect a lot of data and look at it carefully. You do not see particles, you see effects. And then you give those effects a name. Now stop for a moment and think about that. You imagine a tiny object flying around in space, but what you actually observe is a mark on a screen, a response from a detector, a signal. Something changed somewhere and you notice the change. That is already a mismatch. Let me make this more concrete. Imagine a detector sitting on a table. Nothing fancy, something that clicks when something hits it. You turn it on. It starts clicking occasionally. Each click gets recorded. You look at the data later and say, those were particles. But what actually happened? Something interacted with the detector. Energy was deposited. A circuit responded. A signal was produced. At no point did you watch a tiny object arrive, stop, and announce itself. You inferred it. Now here is the next question, and this is where things start to get uncomfortable. Many of you here in this audience will get this answer wrong, but I am hoping many of you will get it right. So, where was the particle before the detector clicked? People answer this confidently at first. Somewhere out there, on its way, moving toward the detector. Okay, but how do you know that? You did not see it traveling, you did not track it, you did not watch it approach. All you have is a click, right here, right now. Everything else is a story you are telling yourself. And that story feels natural because it matches how everyday objects behave. If a ball hits a wall, you know where it was before it hit. You can point to its path, you can replay it in your head. So you borrow that way of thinking and apply it to the microscopic world. That is where the trouble starts, because when you try to push that story too far, it falls apart. You ask which path the particle took, and the answers stop being clear. You ask where it was a moment before the interaction, and the explanations get strange. You ask how it knew where to go, and suddenly you are talking about probabilities and rules instead of objects in motion. At that point, people usually say, well, particles are weird. But maybe the problem is not that particles are weird. Maybe the problem is that the particle story was never the right starting point. So let's keep following this carefully. If particles are real objects, then they should behave like objects, right? They should have positions, they should have paths. They should be somewhere even when you are not looking. That is how objects work. Now ask yourself this. What does the theory actually give you before a detector clicks? It is not a location, not a path, and not a tiny thing moving through space. What it gives you is a set of rules. Rules that tell you what can happen if an interaction occurs. Rules that let you calculate the chance that a detector will respond here rather than there. Rules that connect one measurable outcome to another. Interesting, right? You only get something particle-like at the moment something happens. That should already make you uneasy if you are committed to particles as the foundation. Now, think about how different this is from ordinary objects. If a car passes you on the road, you know it existed before you saw it. You know where it was a second ago. You know it followed a path. You could, in principle, reconstruct its motion even if you were not watching. Nothing like that is available here. Before the interaction, there is no track to rewind. There is no hidden movie running behind the scenes that you simply failed to observe. There is only the possibility that something might happen, governed by strict constraints. Now let me ask you something else. If particles are little objects, what keeps track of them? What tells one particle where another one is? What tells it when to interact? What tells it how strong the interaction should be? In everyday life, you do not need to ask these questions. Objects push on each other when they touch. Forces come from contact. Cause and effect feel obvious. But the moment you shrink things down to particles, contact disappears. Nothing is touching. Everything happens across space. So you quietly add new ideas. Forces reaching out, exchanges, messengers flying back and forth. Invisible mechanisms that make the story feel more familiar. That is not physics doing the work. That is intuition trying to survive. I hope many of you are still with me on this subject and none of you sleeping far back somewhere. I will continue anyway. The actual structure does not rely on little objects sending messages to each other. It relies on relationships that are already built into the system. When an interaction happens, it happens because the conditions allow it, not because a particle decided to do something or received a signal telling it what to do. This is why particle explanations keep needing patches. You say the particle traveled along this path, unless it did not. You say it behaved like an object, unless it behaved like a wave. You say it existed here, unless it only existed when measured. Each exception gets its own story. Each story keeps the object idea alive a little longer. But notice what never breaks: the rules, the constraints, the relationships between measurable outcomes, the consistency of what can and cannot happen. Those do not wobble. They do not need fixing. They do not change their story depending on the situation. That should tell you something about what is fundamental and what is not. Particles are a way of talking about certain events after they occur. They are labels you attach once energy shows up in a discrete place and leaves a discrete mark. They are summaries of outcomes. They are not little pieces of reality waiting in space to be discovered. When you treat them that way, you end up asking questions the theory was never built to answer, and then you blame the theory for being confusing. But when you stop insisting on particles as the starting point, something interesting happens. The confusion eases. Not because reality becomes simpler, but because you stop forcing it into a shape it never had. At this point, it helps to look at what replaces the particle story when you let it go. If you strip away the idea of tiny objects moving around, what remains is not emptiness. What remains is structure, something that fills space, something that responds everywhere at once according to strict rules. This is where the word field finally earns its place. A field is not a thing you can point to. It is not a cloud or a mist or a collection of objects. A field is a set of values assigned to space and time. At every location, at every moment, there is something that can respond, change, and interact. You do not need particles for this to work. When an interaction happens, when a detector responds, when energy appears in a localized way, you describe that event as a particle. That description is accurate as far as it goes. But notice the direction. The particle comes after the interaction, not before it. This reverses the usual story. Instead of imagining particles flying through space and occasionally interacting, the theory describes a continuous structure that sometimes produces localized events. The localization is real. The discreteness is real. The click in the detector is real. What is not required is a tiny object carrying its identity through space the whole time. This is why so many particle-based questions dissolve once you stop insisting on them. Questions like, which path did it take? Or, where was it just before? Lose their grip, not because the answers are hidden, but because the questions were borrowed from the wrong level of description. The theory is not withholding information. It is refusing to pretend. So, now think back to how particles are usually introduced. They are presented as the foundation, and fields are added later as a complication. Something abstract, something mathematical, something optional. That ordering is backwards. Fields are not an extra layer placed on top of particles. Particles are a special way of talking about what fields do under certain conditions. They appear when interactions are sharp, localized, and countable. They disappear when those conditions are not met. That is why the same experiment can look particle-like in one setup and spread out in another. Nothing changed its nature. The structure responded differently because the constraints were different. Once you see this, the particle idea settles into a more modest role. It becomes a tool, a useful one, an effective one, but still a tool. The mistake is turning that tool into a picture of reality itself. That mistake has consequences. It leads people to search for ever smaller objects, expecting understanding to arrive once the list is complete. One more particle, one more layer, one more building block. But understanding does not come from counting objects. It comes from identifying what stays the same across very different situations. That was the real lesson physics had to learn. Very different phenomena, very different experiments, very different scales. And yet the same constraints appear again and again. The same conservation laws, the same symmetries, the same limits on what can happen. Those are not properties of particles. They are properties of structure. When you start from that point, the world looks less like a pile of things and more like a system governed by rules that do not care about your preferred imagery. This is also why the language feels harder at first. You evolved to understand objects. You did not evolve to understand fields defined everywhere. The discomfort you feel is not a sign that something is wrong. It is a sign that intuition is being stretched beyond its usual domain. That stretching is necessary. Because the universe does not arrange itself around what feels familiar. Particles remain useful in practice. No one needs to ban the word or stop using it. Engineers use it. Experimentalists use it. Calculations use it. Results depend on it. But usefulness is not the same thing as fundamentality. Particles describe how certain interactions appear. They do not explain what reality is built from. When you keep that distinction clear, many long-standing confusions lose their force. You stop expecting objects where there are none. You stop asking for paths where there is no motion in the ordinary sense. You stop demanding stories when the structure is already doing the work. Reality is not made of tiny things moving around in empty space. Reality is organized by constraints that allow certain interactions to occur and forbid others. Sometimes those interactions look like particles. Sometimes they do not. Understanding begins when you stop mistaking the appearance for the foundation. That is why particles are a misleading way to think about reality, not because they are useless, not because they are imaginary, but because they are the result, not the starting point. Not comfort, not familiarity, but the truth.